Now let us define the monotonicity of secant slopes. So in the previous video, we derived the definition of convexity for an n-dimensional function, which is phi of some point on the line segment is less than or equal to t times phi of x1 plus 1 minus t times phi of x2. And one thing to notice that in the previous video, I said that t right here is theta, but it should actually be a t. Now let phi be a mapping from real numbers to real numbers. Then phi of the point on the line segment is less than or equal to that expression on the right is the definition of convexity for a one-dimensional function. We're just saying that these x's right here and right here are real numbers instead of vectors. Now we may proceed to derive the monotonicity of secant slopes. So for any 3 points, A is less than B, which is less than C, which are real numbers, define the secant slope between any 2 points, like between A and B, or A and C, or B and C, as S of x1, x2 is defined as phi of x2 minus phi of x1 over x2 minus x1. Now if we define B as a point on the line segment connecting A and C, then we may use the definition of convexity for a one-dimensional function. And note that we're using theta over here instead of t, because theta is a particular value of t. And that's all I have to say for this slide. Now we may use some algebraic manipulations to get from here, then to here, then to here, and from here to here, we say that c minus b is theta times c minus a, because of the way that we defined b in terms of theta. We can rearrange and say that theta times c minus a is equal to c minus b. Now here's where it gets like almost unnecessarily complex, but the complexity is actually necessary, believe it or not. So once you do this, you can cancel out the thetas, leading to this. Then you multiply by c minus a over b minus a on both sides. Then that leads to this jumbled up mess over here. And you'll see why we do that in the next slide. Then we do some more complex algebraic manipulations. So this implies that this is true, then this implies that this is true. So all that implies that this is true, and you may notice that c minus a minus c plus b, that's the same as c minus c is 0, b minus a, that's b minus a, over b minus a, that is 1. Therefore, we're left with this term is greater than or equal to this term. Right over here in this red box, we'd find that stuff. And this is the monotonicity of secant slopes. So it's saying that phi of c, that's the point, the rightmost point, minus phi of b, that's like the middle point, over c minus b. So that's the slope between c and b. And that slope is greater than or equal to the slope between a and b. So how do we interpret this? We say that like we say that the slopes are like kind of like this, then this. So the slope increases, kind of like in a convex function like this, the slope will increase. So the slope over here is negative, but it becomes less negative as you go over here. Then it starts becoming positive and more positive. So that's an example. And yeah, that's the monotonicity of secant slopes.